Hello everyone, today we're going to be looking at a Hardy-Weinberg chi-square problem. So the basis of the Hardy-Weinberg principle states that both allelic frequency and genotypic frequency are in equilibrium unless a disturbance occurs. So how do we test if they are in fact in equilibrium? We use a chi-square test, except the only difference is how we calculate our degrees of freedom. The way that we do this is by taking the total number of genotypic classes and subtracting them by the available alleles. The easiest way to learn how to do this is by example. So in this case, we want to study the allelic frequency of sickle cell anemia of children in a small part of Ghana. Here we see that 756 children are not affected, 200 children are carriers, and 144 children are affected. This leads to a total of 1,100. In order to calculate the Hardy-Weinberg chi-squared, we need to calculate the expected allele frequencies. This is a good time to pause the video so that you can take a moment to try this on your own. In order to find our frequency for S, which we will denote as P, we are multiplying the number of not affected individuals by 2 and adding that with the carriers. This summation is going to be divided by 2 times the population. In the case of allelic frequency B, we are going to be multiplying the affected individuals by 2 and adding the carriers. And then that summation is also going to be divided by the population times 2. And when we plug in our numbers, this is what our allele frequencies look like. So in the case of S, our allele frequency is 0.778, which is also denoted as P. In the case of B, our allelic frequency is 0.222, which is also denoted as Q. And as a quick test to see if our calculated Q and P values are correct, they should add up to 1 when they are summed. And if they don't, then you need to go back to your calculations. Now that we have our expected ratios, we need to find our expected values. With P equal to 0.778, we need to find out the not affected. So in the population, we need to square the p-value and multiply it with the total, and that leaves us with 665.8. To find the carrier population, we need to multiply 2 times p times q times the total, and that leaves us with 379.9. To find the affected value, we need to take our q value, square it, multiply it by our total, and that leaves us with 54.2. From here, it's a basic plug and chug into the chi-squared formula, which is a summation of observed minus expected squared divided by expected. So when we add our respective values into the respective places and calculate our degrees of freedom with 3 genotypes and 2 alleles, we find that our calculated chi-squared value is 246.21. Comparing that to our critical table, we see that our value is significantly larger than the table value of 3.84 at 95%. Therefore, we can reject our null hypothesis, showing that the alleles are out of equilibrium in this population.